Okay, a little bit of background before we begin on the notation for these different variations of sine functions. We can put this to, and you see what I've got here is I've got three different options of where that 2 can go, and each one of these means something different. A 2 in front of the sine could be 2 times sine of x, which is a simplified form of just sine of x plus sine of x. Those are the only 3 ways that we would ever write this. 1, 2, 3. Sine squared x, we've talked about this before. That's taking sine x and multiplying it by itself, which again is the same as sine of x times the sine of x. That's the only 3 ways we would write that, but we typically just stick to this form in those instances. This last one, this third option, is what the focus for this topic is, and that is it's a double angle. Okay? This representation, this notation, cannot be represented in any way like we've seen just now, but what we can do, and you remember this proof from class yesterday, is we can write this as sine of x plus x. Now if we do a little simplifying here, if we expand this sine of the quantity x plus x using the sum formula, we get sine x cosine x plus sine x cosine x. I'm supposed to be using different angles here and here, but if they're the same, then they're going to obviously look the same. Now what I end up with is the exact same term being added to itself, so I can represent this with the 2 in front. And that gives us a brand new property for expanding the double angle for sine. Okay? Just like we can say, you know, we've got this secant squared x equals 1 plus tangent squared x. We've got all of these properties that we've listed in the past. This is a new one. This one involves the double angle on the inside of sine. And as I scroll down here, what you'll see is the different manifestations of a double angle for cosine. So you can see that cosine of 2x has 3 representations for it, whereas sine of 2x was only equal to this one expression. Cosine of 2x has 3 different equivalent expressions. Now, each one of these, once you get past the first one, each one of these 2, here and here, is a different way of combining these 2 terms. I could do a substitution with cosine squared x and come up with this, or if I start back here with this first option again, and I do a substitution with sine squared x, I would end up here. So these three different expressions are equivalent. All of them are equivalent to cosine of 2x, which complicates things because when this is involved in a proof, I have to be thinking about which one of these 3 options makes the most sense to use. Tangent of 2x, you can see here at the bottom, the tangent of 2x only has 1 representation. Make sure you're writing these down in your notes as you go forward so you know how to incorporate